Okay, we are going to see now or continue our discussion about the different kinds of controller. And today we're going to see what integral control does. We will look also at derivative control and the combinations of them. Okay, so a little bit of a background here as the slide shows you. Proportional control produces a constant error because the control signal does not change as the system reaches equilibrium. This is the reason. With this other kind of controller, however, we would like to modify the control signal as long as the error exists. So, if an error exists, we need to change the control. So, changing control is proportional to the integral of the error. So, proportional control is proportional to the error. The more error, the more control. The one integral control is proportional to the integral of the error. So, in terms of the frequency domain, integral control, integral is 1 over s, right? So here's your constant of integration, your gain, and this is the error. So if you multiply the error by 1 over s times the integration constant, this is your control law in the frequency domain. If in the time domain, this is you would interpret it like this, as the integral from 0 to t of the error. So k sub I is the integral gain, and the f sub s is the change in the control signal. In other words, what we are doing is we are imposing on the system this kind of control. So the best thing is to do a little bit of an example in here and then see what we are saying here. Here's the most important part. This is your system, okay? I think by now, since I introduced last time the different components of the control, you should be able to recognize it very easily. So this is the system. You measure something, and then you're going to compare with some set value that you have. If the two signals are the same, the error is 0. If the two signals are different, then you have an error. So we feed this error here, right here, and we put this integral control on that error. So the integral of the error is what is fed back, multiplied by the gain, what is fed back to the system. What is this here? Still, you might have a bit of an issue with that and be wondering, what is that? This is the disturbance. So in other words, this is what causes the system to get out of control. This is the similar, like if you are cooking your turkey and you have it set up to be at 375 degrees, somebody opens the door of the oven and it's no longer 375. Okay, so if there's no disturbance, of course that's best, but obviously you need a control because you need to protect yourself to the disturbances. So this is a unity feedback control, the way you have it in here. So this is our world, you may say the engineering world, the virtual world, where we built our block diagram and we understand the system in terms of mathematical equations, right? That's what this is. In terms of real life, here's what you have. The DC motor, this one would be this, and of course the load, yeah. So this is your system right here. This tachometer attached here at the end on the output of the motor measures how many RPM, let's say, you are producing here. So it takes that measure here, see back, and then compares it to your set value. It's doing this kind of thing. The difference between these two is fed to this, we'll call it power amplifier, which would be the one that executes the control, actually. So this integral control has to be inside of it. This is your physical system, the feedback, the comparison in here, and the control here. I hope that by now it is second nature to you, that you have this. These are the components of the control system, and what we strive in the end is to obtain a result in here that would be the combination of the system plus the control. So the combination of the system and the control produces a new control system, see? And that is supposed to do what you want to do. Now, remember that in systems, the transfer function concept is always the relationship between an output and an input. So if the output omega s is the result of the output we get from the system, as it relates to the original signal, you have this transfer function. So you have the transfer function with the integral controlling here. If you have the system relating, the output of the system relating to the input, to the disturbance, you have this other transfer function. So the idea here is, how would we find this k here? This is an example of this was a first order system. As you can see, s is to the first power. But if you have it on a second order system, for example, the transfer function is like this now. You have the motor in here, a DC motor. You have a disturbance torque in here, and then this is where you measure it. You feed back to this amplifier, compare it to the command, to the desired value, and there you have your control system. So this whole thing that you see here in words and in physical components, it's expressed over here in terms of the integral control plus your system. And here, as an example, are the two transfer functions. So you could see why we spend quite a bit of time in obtaining the transfer functions. Because at this point where we are designing the controls, either you are given the transfer function, or you have to find out what it is. And to do that, you are well equipped with tools on how to find the transfer function. But we are basically working with this. In fact, some books don't have much in terms of the background of 171 or the derivations, a lot of derivations from the system, but they start with the state space representation or with the transfer functions. And so from now on, that's where we need to concentrate our attention. In the case of integral control, the system oscillates, creating instability. So you fix the error, but the system oscillates. Mathematical problems also with integral control. Final value theorem cannot be applied. And integral control improves a steady state, but it produces an unstable system. So it has an undesirable effect also. So it's just like everything in excess is bad. Let me put it that way. So you might have a little bit of integral control, enough to do and correct the error that you need. But if you put too much of it, the system will go unstable. Also, it slows down the system, corrects the error, but it will degrade the transient response. So it means the system is not going to react very quickly. In fact, becomes slower and oscillates. So it doesn't reach a steady state in one scoop like proportional control, but this would oscillate. Okay, let's go to the next type of control, derivative control. You see the background is integral control produce a control signal error and unstable system. Now we would like to make a controller that will react to the derivation of the error, to the derivative of the error, with the derivative control law. This is the equivalent of inducing damping in your system. So you begin to see that all three complement each other. Proportional control is fast. Integral control corrects the error, but you put too much, the system oscillates. But it's like antidote. You know, to correct that, you put derivative control. Derivative control is damping in the system. So this one would actually introduce elements that dissipate energy. So the derivative is, the law is you have the gain for derivative control is, remember ddt, so it's derivative, times the error. So this is the derivative control law. So look on the bottom now, your control system, if you have a PD controller, is going to look like you see on this equation right here. It has the proportional constant, the derivative constants times S, and then times the error. You see, that's the control law. If you have you could write this in terms of a rate of time or derivative time. On the bottom one, you see PID control. It means you have a proportional component, then you have an integral component, and then you have a derivative component, and all that multiplied by the error. So by now we are seeing that with these three types of controls, like I said, it's as if you have several ingredients to produce a certain result. How much of it you should put, or maybe you should not have one of those in the system. That's the question. For example, here, if you have a proportional derivative control for second order system, you have in here a servo mechanism that has this kind of transfer function for the system. So in here, if you have a disturbance, it will correct. It would improve the transient response, and in this case, no integration is required. So depends what the system is, what it does. So it depends heavily on this transfer function. So what you are seeing here is the product of this times this and those two combined with the feedback loop. That's how you get this. Remember, the feedback loop transfer function is the result of a feedback loop transfer function. This is stable system. The rate of action does not affect the steady state response. So PD controller for a second order system is good. The results are the same as those with proportional control here. Zero offset error. So the deviation is proportional to the proportional control. If you have this control, PI control now, the one that we were just in is called PD control. This one is PI control. Okay, here's the background for this. Proportional control introduces steady state error. Integral control corrected the steady state error but degraded the transient response. Objective: can we combine the instantaneous response characteristics of proportional control with the zero error steady state characteristic of integral control? If you do that, you will have this, see? And you can put it in different forms, this control law. So you could do the expression of this in this form or this form using these other variables, like t sub I is the reset time. Integral action resets the controller in the presence of a disturbance. 1 over t sub I is the frequency with which the integral action repeats the proportional correction. Integral action will not react instantaneously to a zero error, but continues to correct. So this is PI controller. Now, the damping ratio is an interesting concept because you could have a system that has the poles on the left hand side, and if you get off of the real axis, then you have damping. And damping, this is the way we express the damping ratio. And in terms also of the proportional and derivative gains. So proportional gain can be large to reduce steady state deviation. So translating in other words, if you have a big error, you need big control. derivative control can be used to achieve an acceptable damping ratio, meaning you introduce dissipation on the system. And then finally, KD helps stabilize the system by adding damping. Now here you have an equivalent derivative action. So you could have different combinations of this PI PD controller. So in this case, you have this tachometer that measures the angular velocity of this load, and then this is used to produce differentiation. So this is an equivalent circuit as a whole to a PD controller. Okay. If we look at the transfer function here for this, the numerator has no dynamics, so the system is slower than one with pure PD control. K1 and 2 can be chosen to give the desired damping ratio at the steady state deviation. The control system is stable if I, C, and K are positive. So you have this kind of a response if you put a unit step input. Here you have a PI controller. So we're looking at different kinds of examples. This is a PI controller. What are the advantages or conclusions of using something like this? Because you can see this is the proportional gain, this is the integral gain, right? Conclusion: steady, stable for positive values of Kp. Response to the step input equals to make a steady state. Offset error 0. Response to unit step disturbance also has 0 error. Kp allows the damping ratio to be selected without fixing values of the dominant time constant. And then, so these are just to indicate what the reaction is to the different values of the time constant. And of course here it says you pick the proportional and integral controls. Here we have second order system, for example. If you do the different this proportional control for a second order system, so you can see that the control, you just don't go and throw the proportional or integral or so. It depends what the original transfer function is. But what we are seeing here is we're trying with different transfer functions. For example, is this in this case, steady state performance is good if K proportional and K integral. Problems: for a small c, Kp must be large in order to satisfy the fact that c Kp minus I Ki should be bigger than 0. So conclusion here, hard to implement. If Kp is bigger than 0, the time constant may not be satisfactory. So you get the trade-offs in there, and what I'm outlining in there are the conclusions and observations. The analysis of third order equations done with Root-Locus method for this. Okay. This is an interesting mechanism, and you might appear at first all overwhelming, but I think this kind of controls, this kind of problems are good for your final projects that you might be thinking about. I will be giving you some instructions a little later, but this is a good example for a final project for the class. At first it may appear overwhelming to you, but I'll explain it to you, the components, and then it won't be. This is a liquid level control system, and in here what you have is that this is the level of the fluid, right? And in here the feedback is going to be like, in this case air goes here. Air is a fluid. If the level is raising, so you get pressure here. If you get pressure here, you're gonna switch this this valve at some point, because that's what it has. The supply of water is coming here, and this would be the actuator that opens and closes this valve. So if the level goes down, this would go the other way and let the pressure flow come this way. If you don't want any, if it's raising, the water raising, this pivoted beam does the opposite. So the whole entire system here is designed to control this valve that either gives water to the system or closes the valve. Okay, so this is another example of application of this. So I'll just show you the way the equations are for this particular valve. This is done with a different method, just the block diagram method in here. And so you derive this is the control differential equation of the system. Is a first order system, and then you have case dFdy and case of 2dFdP. So in this case, you see, this is how that system would be. System is over here, and you have this controller here, but you see here's the proportional control and also integral control, and then this compare in here. We would like this error to be as small as possible, because that's what the objective is, to make the system operate at that point. Okay. Finally, PID controller. This one, do you see here you have your system, and then we're gonna have all three of those. A little bit of a background. The position servo mechanism designed with PI is not satisfactory, because if there is oscillations generated, there will be oscillations generated. Question is, improve the oscillatory condition of integral control and make the controller aware of zero error and reduce the deviation of the value that we. So this would be the the setup on how you build a PID controller onto your system. So you can see this has a component that's integrated, one that is the derivative and then the proportional control. So the combination of these two is what you have down here as transfer function. Okay? So any combination of these controllers can be made depending on what the system requires. PI control is proportional plus integral control. PD is proportional plus derivative control. Or you can have a PID controller, which is a combination of all these three. And you have the control law is over here. So depending upon the action requires, the gains will have to be adjusted to the required control. So that is the conclusion of this presentation on the three different kinds of controllers that we can have.